Okay, so we did our first Nyquist plot on Friday. So one of the things to keep in mind is that the Nyquist plot is very much related to the Bodie plot. So this was the Bodie plot for our system. Our open loop system was a standard second order underdamped system. So going back to where we started with this problem statement, where were we? Yeah, so we had, all right, create the Nyquist plot and analyze stability for the second order underdamped system. Bodie plot should be reviewed for everyone in terms of what that looks like, and then the new information was taking what's in the Bodie plot and how do we turn that into a Nyquist plot. And so we showed this Nyquist plot for this example, and then right before we adjourned class, we looked at software tools to produce the Nyquist plot, and I accidentally typed in the transfer function incorrectly, as someone noted after class. So let's redo that. Okay, so just to show the Bodie plot for this so everyone's up to speed, this is a standard second order underdamped system. So this should look a lot like our sketch we had, which it does, right? So standard resonance at the natural frequency, right? Nothing new here. And then in terms of turning this into a Nyquist plot, we went through the rules for plotting that, and then this was our Nyquist plot. So it has this shape. So as a reminder, this is for frequencies going from, this is S is equal to I, 0 to the right, all the way up to SI infinity. And then this is going from SI negative infinity all the way up to SI 0 to the left. Right? So this is what completes our contour. And then I believe the very last thing we did is we evaluated and said, all right, what we're saying here is that this system is in a closed loop. And I had to zoom through this pretty quickly. So I want to take a second to go through this here. Okay, we have G of S is in a closed loop. So we analyze the open loop system, which is G of S. Right, and we're saying if the system is in a closed loop, means it's in, or we could write a block diagram that says it's in this configuration. All right, is this system C over R stable? Okay, so we already know that G of S is stable, right? Because we're looking at this, we say second order underdamped system, all the poles on the left half plane, the system's stable. Now the question is, if we have this in a closed loop, means we assembled all the pieces of the hardware that are required to put this in a closed loop, is C over R going to be stable? And so to do that, we look at the Nyquist plot and we evaluate this function. So this is, as a reminder, this is number closed loop poles in right half plane. This was number open loop poles in right half plane. Okay, so the discrepancy between these two, open loop poles are the poles of G of S. Closed loop poles are the poles of C over R. So the number of closed loop poles in the right half plane is going to be some sort of function of the number of open loop poles in the right half plane, and then also is going to be the number of counterclockwise encirclements of -1 of the Nyquist plot. All right, so for this example, we said, all right, we know the open loop system is stable, no poles in the right half plane. We look at the Nyquist plot, we say, all right, does this Nyquist plot ever encircle the point -1? Here's -1. The black line is the Nyquist plot. We say, okay, this never circles that. That means that there are 0 encirclements, and that means that we have 0 poles in the right half plane. So that was our analysis from Friday's lecture. Any questions? Dan? About -1. Yes. so -1 is the point of interest. Just to highlight that, it may be tough to see in the back, but there's a little red cross at -1, and that's just highlighting that's a point of interest. And so Nyquist plot will automatically generate that little red cross for you. Zero encirclements. Yep, this blue line never encircles the red cross. All right. So that was one consideration. The notes itself give like a step, like we step by step went through this where writing on top of our plot. The notes go through kind of a long process of getting to that. So I'm going to jump forward here a little bit. All right, so it may be worth considering what happens as we increase the gain. So before, the previous example, we just had the case of this k out front is equal to 1. Right? And so we may want to consider what happens if we, say, make k greater than 1, or if we make k less than 1, does that affect the stability of our system? Right? That's an important consideration we look at a lot of times. Does gain affect the system? All right, so going back to what we've plotted thus far, all right, so this here was magnitude of g when g of s is equal to omega n squared over s squared plus 2 zeta omega ns plus omega n squared. All right. So how would this Bodie plot change if this instead became k times this, and say k is greater than 1? What's going to happen to the Bodie plot? Justin is pointing upwards towards the sky. Shift up, right? Okay, so that's going to be the magnitude, right? What's going to happen to the phase? Stay the same, right? So the gain up front, if this gain is greater than 1, it's a positive number. The phase of just a gain is 0 phase, right? So the phase plot is going to remain the same, and then the magnitude plot is going to move in the upward direction, right? So if we have a gain greater than 1, this whole plot shifts upwards. Right, so this would be k greater than 1. And then, of course, if we decrease the gain, say move it less than 1, it's just going to shift it in the other direction. All right, so this would be k less than 1, right? Okay, so multiplying by a larger gain, a gain larger than 1 shifts the magnitude plot up. Gain less than 1 shifts it down. And so since we haven't changed the phase information, it really doesn't change the shape of this Nyquist plot. All it does is it either dilates it or it contracts the Nyquist plot. So if we have, let me try and match my colors here. We have k greater than 1. Right, so what that's going to do is it's going to take the same exact shape for the Nyquist plot, and now it's just going to be larger, right? Because the gain, or the vector length for all these points which we considered, is now a larger number. All right, put my arrows to show what direction this is circling, and this would be k greater than 1. All right, and then the opposite would be true if we have k less than 1, right? We'd have actually contraction of the Nyquist plot. So same basic shape, to the best of my drawing abilities. This would be k less than 1. And just to show that in software, if I were in MATLAB, all right, change G, and say instead of this being, say 100 in the numerator, I just change this to 200, and say hold on, Nyquist G, right? So by saying the numerator going from 100 to 200, I've doubled the gain. I said I have a K of 2 out front. So I have the previous Nyquist plot was the blue line. The new one is this orange line, right? And so we've just basically taken the Nyquist plot we had before and just expanded it by a factor of 2 about the origin. And so basically just an expansion, right? And if oppositely, if I wanted to say G is now 50, so that'd be 1/2, a gain of 1/2 on the system. That would be this smaller Nyquist plot, right? So just exactly the same shape, just expanded or contracted. Any questions about that relationship there? Okay. All right. So then going back to this discussion about, is the system stable? Is it unstable? Right? So we look at the closed loop system, we say, all right, is the system stable? We're looking at number of poles, open loop poles in the right half plane. So we haven't changed the pole locations of our open loop system by changing the gain, right? So P stays the same. Have we changed the number of encirclements for this particular problem? Did we change the number of encirclements of the point -1? Yes? No? I see people shaking their head. No. Okay. So yeah, exactly right. So if we look at like the neater drawing of this, is what's in software, we see that this plot, regardless of what the gain is just going to expand about the origin. It's never going to encircle the point -1, right? It's gonna, this point -1, as we increase, is going to get deeper into this kind of, about the butt crack of the Nyquist plot here. It's going to get deeper in here, but it's never going to be encircled, right? So it's never going to go around this. So this is saying that regardless of what the gain is, this system is going to be stable. And we could have seen this too if we were looked at the root locus plot for the system. So as a really quick root locus plot, we have complex conjugate poles for the system. And we would draw the root locus plot, it would be a plot that looks like this. All right, so as the gain increases, the poles are going to keep on going to larger and larger imaginary apart, but they're never going to cross into the right half plane. So these give us complementary information. These two. Yes, Sarah. Exactly. It's not going to hold for the next example I'm going to give. Yep, just for this example. Okay. Any questions about that analysis for this system? Okay. It's just second order underdamped system. So it was going back, just this right here. All right. All right, so next example. All right, so slight deviation from this example here. We have, really the only thing different here is we have an extra pole, and this pole is at the origin for this example. So slight deviation, it makes a big difference in terms of stability though. Okay, so we have, also I'm giving this as a generic gain here. We'll start out with k is equal to 1 to begin with. All right, so same question, plot the Nyquist plot and examine the stability of the closed loop system for this open loop transfer function G1, G2 is equal to k times omega n squared over s times the quantity s squared plus 2 zeta omega n s plus omega n squared. All right, so Bodie plot for this should be review again, but we have standard Bodie plot. This is mag, G1, G2. This is phase, G1, G2. And so magnitude, we're going to get a negative 20 dB per decade slope everywhere because we have that pole at the origin. All right, and then somewhere in here, at the natural frequency, we're going to have a change in this slope, right? And it's going to go from negative 20 dB per decade to negative 60. And it's going to have a small, resonance at that natural frequency, right? So this is what our magnitude plot's going to look like. Phase information, we get negative 90 degrees everywhere because of the pole at the origin. And then the second order ramp system is going to cause a change in phase from negative 90 to negative 270, centered around this natural frequency. Okay. And then the procedure we did for the previous one, we're going to follow up for this one as well. So for the previous one, what we did is we looked at just a few frequencies of interest to plot the Nyquist plot. So we said, let me do a different color just to make this pop a little bit better. All right, we'll look at a low frequency. We'll call this omega A. We'll look at something kind of a medium frequency. All right, we'll look at a frequency rate at the natural frequency. And then frequencies above the natural frequency. All right. So then we're going to plot the Nyquist plot for this. Plenty of space here. Okay, so looking at these 5 frequencies of interest here. Okay, so at omega A, right, we're going to have a magnitude that's large, right? This is a magnitude that's greater than 1 because it's over 0 dB, and it's basically just a large number for lack of more, more specific terms, right? So large magnitude, phase angle of negative 90 degrees. And also we see this is asymptotic. So as I go to lower and lower frequencies, the phase asymptotically reaches negative 90 degrees, and the magnitude keeps on getting larger. So if I go down all the way to 0 frequency, the magnitude is actually equal to infinity, right? If I keep on going farther and farther left. So what this is saying is that we have our Nyquist plot is coming from way down in this direction, right? Infinite magnitude, phase angle of negative 90 degrees, which is basically at negative I, or negative I times infinity. So what we're saying here is that the Nyquist plot is coming from this direction, and it's coming in here. So we could point out and say, all right, here is approximately G of S evaluated at I omega A. Right, so phase angle is slightly less than 90 degrees because it only asymptotically reaches, slightly less than negative 90 degrees because it asymptotically goes to negative 90. But this would be G of I omega A would be this vector. But if we were just going to continue this, we see higher and higher magnitude, phase approaching negative 90, which means that if we look at G of I 0 to the right, that is way, way down. That's infinitely in the negative I direction. Any questions on that thought? This is something that gets a little more abstract. Okay, so if I look at then omega b, what I get is, this is just an asymptotic approximation. So if I were to look at the real phase plot, this would actually be rounded off a little bit. All right, so if I look at omega b, I have magnitude less than 1. I have phase a little bit less than negative 90. Right, so the phase is going to get smaller, magnitude is going to get smaller. So this is a vector, say, just as approximation. And here, as kind of a rough approximation, get this general shape. And now if I look at the case of omega c, I have a magnitude where I have this resonance, so the magnitude increased slightly, right? Still less than 1 for this particular example. And then it's a phase angle of negative 180 degrees, right, at this resonance. And so what we have here is a vector. Negative 180 degrees is due west. Magnitude increased a little bit, g of I omega c. And then as I keep on going on, magnitude is going to continue to decrease. Phase is going to asymptotically approach negative 270. So if I were to fill in the rest of this Nyquist plot, I'd be following these vectors here. And then it decreases in magnitude, and then it closes at negative 270 degrees. And this was, sorry, I forgot to label this. This would be step 1. So this would be g of I 0 to the right half plane, or g of I 0 to the right, all the way to g I infinity, right? So as frequency goes to infinity, magnitude goes to 0, but the phase angle never goes past negative 270 degrees. Dan. Now you're thinking of real poles. So if you have second order underdamped systems, the how long it takes in terms of frequency for you to go from whatever the current phase is to negative 180 is dependent on zeta, the damping coefficient. So if zeta goes to 0, it actually very abruptly changes. If it goes to 1, it gets more similar to what a second or 2 real poles and how they behave. No, that's for just a single real pole. Justin.
Can you explain again how you're going from the phase plot? Because why is g I omega a not just straight down? It's kind of off the imaginary axis.
Yeah. So your question is, why is this vector here not negative 90 degrees, right? Yeah. Okay. So this is a just approximation, and maybe just a bad approximation, but what we're doing here is we're looking at this asymptotically approaches negative 90. So it actually never goes above negative 90. So above negative 90 is the fourth quadrant here, right? If it's slightly below negative 90 is the third quadrant. So it's. That makes sense.
And then how did you the one that's negative 90
So let me draw. So when you're at the natural frequency, the phase of a second order underdamped system is negative 90. And so we have negative 90 coming from the pole at the origin, plus another negative 90 coming from the fact that we are evaluating this at the frequency of the natural frequency. So if I were to draw this omega c, this is crossing directly at negative 180. So at this frequency, the phase is negative 180, which is a vector going due west. All right, so that was step one. Step two, evaluate at s is equal to negative I infinity all the way to s is equal to I 0 to the left. All right. And so we said in Friday's lecture that when we want to do this, all we're doing is we're mirroring the Nyquist plot about the real axis. So there's no real mystery to this. Just flip it about the real axis. So I'm just going to take this plot and mirror it about the real axis. So some points of interest here to help you orient yourself. So right here is G negative I infinity. Way up here is G I 0 to the left. Okay, step three. So consider transition from G I guess S is equal to zero I to the left to S is equal to I 0 to the right. Okay, so in the previous example, this was not a concern. All right, so a few items here to keep in mind is that one, Nyquist plot must make a contour, or must be a contour. All right, so if we look at the previous example, Nyquist plot, right, this formed a contour without having to evaluate step three. If we look at this case, it doesn't quite make a contour, right? So this is increasing frequency. I think this is important to note. If we look at GI 0 to the left, it doesn't match up with GI 0 to the right, right? So we need to figure out how this contour closes. So Nyquist plot must be a contour, and here, for this example, we have discontinuity for S is equal to I 0 to the left to S is equal to I 0 to the right transition. Okay, so if this has to be a contour, we know that as we march along the Nyquist plot, that this line has to somehow connect to this line. But the question that we don't know is, does this close in the right half plane, or does it close in the left half plane? The other thing we know is that it closes at infinity. So if we look at the magnitude at G of I0, or really low frequencies, the magnitude is infinite. So we know this is going to be an infinite contour. We just don't know if it closes in the right half plane or the left half plane. And that's important because when we evaluate stability, we're looking at whether or not this encircles the point -1. So if it closes the right half plane, it doesn't necessarily, for this gain, doesn't add encirclement. If it closes the left half plane, it does add an encirclement, right? So we need to know this information. Okay. So what we're going to do here is we're going to go back to our definition and we're going to look at the problem. So we said that before, when we're doing the Nyquist plot, we're evaluating S about a contour C that is in the entire right half plane. So we said, okay, let's draw our contour. We care about if poles are in the right half plane, so let's make the contour our entire right half plane. So we make this contour like this. This is what we called C. And if we were to evaluate the phase angle, we'd be looking at, all right, here's some sort of test point S. S is marching around in the clockwise direction. Let's look at vectors going from our poles and zeros to this point S as we go along in space. So if we were to just use this standard contour we had for the previous example, we'd run into a problem, not by evaluating the vectors going from here and here to that point S, but by evaluating the ones at the origin, because this contour goes through the origin, which creates a singularity point. All right, so what we do is we do a little trick. Instead of the contour that we showed before, we just slightly modify it. So we have same basic shape. These are all our poles of our system. And we're going to hold the same contour going along the negative imaginary axis. When we get to the singularity point here, we're actually going to make an infinitesimally large bump around it. And then we're going to then continue on. All right, so instead of looking at whether or not the poles are in the entire right half plane, we're saying, are the poles in the right half plane minus this infinitesimally large bump? Sierra? I'd have to think about that. It shouldn't. It shouldn't, because it's just looking at, is there a pole? Like what we're doing is saying, instead, is there a pole in the entire right half plane? We're saying, is there a pole in the right half plane minus this little section of it? I'd have to write that out by hand and see, but it shouldn't make a big difference. All right. So before we said that we have important points of S is equal to I 0 to the left. S is equal to I 0 to the right. S is equal to I infinity. S is equal to negative I infinity. We're going to have the same important points now, except one extra one. So just filling in all these points. Our now extra point we're going to care about is S is equal to just 0 to the right, no I, right? So this is along the real axis here. All right, Dan. Yep. Yeah, so the Bodie plot, we have this relationship between the Bodie plot and the Nyquist plot for positive frequencies. In mechanical engineering, we don't talk about negative frequencies very often unless we're talking about the Nyquist plot. Your friends in electrical engineering, they work in negative frequencies all the time. But there's no real mystery to it. It's just that the phase flips sign. That's it. The magnitude stays the same. And that's why we're reflecting this about the real axis. All right. So what we're doing here is we're trying to understand this transition. We're trying to understand this transition as we go from evaluating G, I0 to the left, to G0 to the right, to G I0 to the right. And so if we look, we're going around this contour in the clockwise direction. So this is exactly the sequence at which we're going around, right? First we hit Si0 to the left, S0 to the right, Si0 to the right. Right? That's the sequence. So we're caring about this. And in particular, we're going to care about the magnitude of these in sequence, right? So this is sequence 1, 2, 3. Right. So if I want to know the phase information of this, I'm looking at vectors going from all these pole locations to this point. Right. So if I'm looking at I0 to the right, or to the left, that's right here. So I'm looking at the phase contribution of a vector going from this pole to here, right? And I can call this a, theta. I don't actually know what this is because we haven't put numbers on this, but this phase angle would be theta, right? So if I look at phase contribution, there are no zeros in this problem. If there were, this would not be 0. This would be some other number, but in this case it's not. So the phase contribution would be 0 minus then theta. This bump is infinitesimally large, so the phase angle coming from this pole is going to be negative theta. And then if I look at the phase angle from the pole of the origin to Si0 to the left, that's a vector going straight down. Right? So this is a phase angle of negative 90 degrees. So I add this all up. This is a phase angle of 90 degrees when we evaluate Gi0 to the right. And this is what you should get. You should get this to match what you plotted already, right? So if we look at Gi0 to the right, to the left, at a phase angle plus 90 degrees. All right, that is a match. You did something wrong. All right, and so we can do the same thing for this other case. Let's go in sequence here. All right, so then if we look at G0 to the right, phase angle of 0 from the zeros, theta minus theta from the two complex conjugate poles. And then if we look at the vector going from the origin to this location, this is due east. So that's a phase angle of 0. So this is 0 degrees. Last one. All right, now we're evaluating all these vectors going to this point. Si0 to the right. This is plus 90. So we're going to get a phase angle of negative 90. Okay. So what does this mean in terms of relation to our Nyquist plot? What this is saying is as we transition from I0 to the left to 0 to the right to I0 to the right, the phase angle is going 90, 0, negative 90. So this means that we're going from 90, 0, which is over here, negative 90. So that means that this Nyquist plot is closing in the right half plane. Right? If we were to evaluate this and we would have gotten 180, that means it would be closing in the left half plane. But since it said 0, it's closing in the right half plane. So just to finish this Nyquist plot, that means that this closes, and we often denote an infinite loop by a dotted line. So it's closing in the right half plane. And that finishes off the Nyquist plot.
Can you explain that again?
Okay. So we had we have a sequence, right? We're looking at I0 to the left, 0 to the right, I0 to the right. All right. So we already have these points already figured out. Gi0 to the left, Gi0 to the right. We want to know where is Gi or G0 to the right. We evaluated and we said it's at 0 degrees. So as we transition from this point to this point, and we know we have to go through 0 to the right, so that means it's over here. Does that make sense? Ben?
How would you draw that if it closed to the left here?
It would just be
Would be like the same thing with the opposite.
Just be like this. And we're not going to quite get to this handout that I wanted to go through today. that we'll reserve for Wednesday. You'll see an example in the handout of closing a left half plane. Okay. All right. So really quick in like the remaining 2 minutes here. If we evaluate stability for the system, all right, so for current gain, for K is equal to 1, we would get stability as this is the number of closed loop poles in the right half plane, open loop poles in the right half plane, and counterclockwise encirclements of the point -1. So for this example, all the open loop poles are not in the right half plane, right? We have 2 complex conjugate poles and 1 at the origin, right? So P is equal to 0. If we look at number of encirclements of -1, this does not encircle -1, right? So this system is stable for this configuration. All right. So now what happens as I increase the gain on the system? What's going to happen in the Nyquist plot? Expand. And we can increase the gain large enough so this actually encircles the point -1. Right. In what direction is this encircling the point -1? Clockwise, yeah. Clockwise. And how many encirclements do we have? 2, right? So if you don't see the 2, we have 1, the small encirclement, and we also have the infinite encirclement of -1. So if we have K greater than some K critical, we're going to have then when we evaluate Z is equal to P minus N, we're going to still have 0. We haven't changed the open loop system at all. And we have -2 counterclockwise encirclements or 2 clockwise. So if it's clockwise and we want to know counterclockwise, just put a negative sign out front. So that means that we have 2 poles in the right half plane. So 2 closed loop poles in right half plane and unstable. Carson.
What we ultimately get is Z that's negative.
You can't.
Okay.
Yeah. Because Z is negative, you did something wrong in your work. Sarah. Oh, yes, we will have to wait till Wednesday to do that. So we know this intersection point. Right. So and then if we have a gain of, let's say if we gain of 1 and we don't know what should the gain be, so it's just now it circles it, we can actually measure this off. And it's just 1 over this intersection point. We'll talk about that on Wednesday. Yes?
Like the point of doing these is just so like if you have a really complicated system and multiple poles, you can find if it's stable or not.
Yeah. Okay. So that's it for today. I wanted to